Today, I would like to discuss proof-theoretic semantics in the context of substructural logics. This is based on joint work with Eugenio Landelli and Mattia Petrolo. First, a quick recap on proof-theoretic semantics, or PTS for short. I believe it can be viewed from at least two perspectives. The first perspective sees PTS as a formal semantics where the notion of truth is replaced by the notion of proof. And this comes with some characteristics that have been pointed out by Schroeder-Heister and Contu, among other people. There is a transmission view of consequence. So similar to how truth is transmitted from assumptions to conclusion in the classical semantics, in PTS we would have a similar transmission effect, only with proof instead of truth. And closely tied to this, we also have a placeholder view of assumptions. So assumptions do not retain their hypothetical nature, but are instead explained away in terms of closed proofs. So if you're familiar with PTS, you probably recognize this kind of semantic clause here, where on the left we have a ground support relation between assumptions gamma and a goal or conclusion G. This has to be supplemented with a so-called base that gives us kind of the proof conditions for the atoms. It is common to later then generalize over the support relation in a base in order to define logical validity. And on the right here, you see this transmission between proofs of the assumptions gamma in an extended base B prime to proofs of the conclusion G in the same extended base B prime. And notice that on the left side of the entailment sign here, we don't have anything, so we are dealing basically with closed proofs. Now, I believe this first perspective on PTS is very appealing for a number of reasons. It is very familiar, so we maintain most of the framework from classical semantics. We can explain it very concisely by saying, well, we just kind of replace truth with proof, and it fits very well with the BHK interpretation of the logical constants. In fact, a very influential conjecture in PTS states that intuitionistic logic is the logic of PTS in the sense that it is both sound and complete with respect to PTS. Some approaches that I think are examples of this first perspective are Pravitz's original proof-theoretic definitions of validity from the 70s, although in more recent papers, he doesn't seem to endorse the placeholder view of assumptions anymore, at least not explicitly. We have also so-called base extension semantics from Sundqvist. I'm going to talk a little bit more about it later on. And we have the general proof-theoretic validity of Stafford and Barroso Nascimento. A second perspective on PTS sees it as a kind of a realization of perhaps a more broader philosophical program which seeks to explain meaning in terms of use. Here, the core idea is that we select some inference rules as fixing the meaning of the logical constants by expressing the kind of the canonical ways in which we use these constants in our deductive practice. And then we add on to that some kind of background semantic requirement that we may feel should be placed on expressions as long as they are claimed to be logical expressions, such as this requirement of harmony. Now, I should point out that the second perspective is not necessarily in contraposition to the first one. After all, we may consider the canonical rules here as being essentially proof rules, in which case we will just fall back into the first perspective. But the point is that we don't have to. So with these two elements, we seem to have all the necessary ingredients in order to formulate a formal semantics, at least for the logical constants. One that is not tied either to the transmission view of consequence or to the placeholder view of assumptions. Now, some approaches that I think are examples of this second perspective are this proposal by Schroeder-Heister in 1985. There is also the discussion by Dummett in the logical basis of metaphysics, and hyposemantics, which is short for hypothesis, from De Campos Sons. In the next minutes, I'm going to explain a proof-theoretic semantics for a substructural logic, and our proposal can be seen as a natural development of the second perspective, which is why I wanted to make the distinction in the first place. Okay, so a quick overview before we go into the details. Our semantics centers around a notion of validity based on the elimination rules. And the main idea can be expressed as saying that we have consequence from assumptions to a conclusion whenever anything that can be extracted from the conclusion can also be extracted from the assumptions. Validity here is considered to be a property or an attribute of arguments. So I invite you to imagine that the picture here inside this box on the left, we have an argument that goes from some assumptions gamma through some arbitrary inferences A towards a conclusion G. And in order to evaluate whether this argument is valid or not, according to our main idea at the top, we first need to assess what can be extracted from the conclusion G. We may think that we do that with the help of our canonical inference, that is the elimination rules. For that, we may need then some auxiliary assumptions delta I for the minor premises of elimination. And then with the help of the eliminations, we somehow get to a consequence Zi or zeta I. Now, we will have then that the argument here is valid if for any such consequence that can be extracted from the conclusion, any such consequence zeta I, we can also extract zeta I, but now from the assumptions gamma. And we may think that this is also done with the help of our canonical elimination rules. And in order to be fair, we supply or provide here the same auxiliary assumptions delta I that were used in the case on the left. So validity here is predicated on the existence of this kind of transformation or function or construction or some other thing that takes us from what's on the left to what's on the right. And this is very roughly the main idea for a notion of validity. But I think, I believe you may already notice two things here. One is that there is no particular semantic value being necessarily transmitted from the assumptions to the conclusion. And second, we are not replacing the assumptions with closed proofs. And since our assumptions are kind of first-class citizens, it is very straightforward to try and capture some substructural features by means of different ways to collect and handle the assumptions. More precisely, if you were to collect the assumptions into multisets, and the transformation here is required to preserve the multiset of assumptions, then we should get some kind of linear logic, because the assumptions here are behaving as kind of resources. And this is what I would like to show next. So the target logic is going to be a fragment of intuitionistic, multiplicative, additive linear logic. We have three connectives. So we have a multiplicative conjunction, an additive disjunction, and the linear implication. In order to stay close to our semantic framework, we use natural deduction. This is perhaps a little bit unorthodox, since linear logic is usually formulated in a sequent calculus setting. But there are some works in the literature that deal with linear logic formulated in terms of natural deduction, as well as the associated normalization results. We have, for instance, this doctoral thesis by De Medeiros. There is a very well-known paper by Negri, also a dissertation by Martins, and a paper by Zimmermann. And I'm sure there are many other works that I'm missing here. Now, I'm cheating a little bit because we actually need a natural deduction in sequence style. And this is because we need to be explicit about the elimination rule here for the additive disjunction, where the side assumptions gamma are actually shared between the minor premises, such that the consequence of the rule depends on a single copy of gamma. But in order to avoid throwing a lot of symbolism at you, I'm going to mostly omit all the gammas and deltas and turnstiles and sequence. And I will try to sound a word of warning whenever this shared context phenomena is of importance. Okay. Now, before we carry on to the semantics, I think it is useful to recall some results. In particular, this result here, which is a corollary of a normalization in natural deduction. It deals with this notion of track. We are going to see in a moment what a track is. But here suffices to say that tracks cover all the occurrences in a derivation. Any derivation has at least one main track, which ends with the conclusion of the derivation. It may have more than one main track, and it may also have so-called tracks of higher order as we go up the derivation towards some subderivations for some kind of minor premises. This result states then that for normal derivations, the tracks can be divided into three parts. So we have an analytic part, which is essentially just eliminations. We have a base segment separating the analytic part from the syntactic part. And the syntactic part is essentially just introductions. Any one of these two parts, the analytic or the syntactic part, may be empty. For the tracks, I thought it might be more interesting to actually show you an illustration instead of a definition. So here we have a normal derivation. This is minimal logic. So the usual disjunction and conjunction. And here at the bottom, I have laid out vertically the four main tracks in this derivation. So the derivations are composed of occurrences, of formulas, a single occurrence in the derivation may appear in more than one track. So we may conceptualize a track as a way to trace the occurrences inside the derivation, all the occurrences, or as a particular way to read the derivation. So for instance, in this case here, if we start with this major premise of elimination, instead of perhaps more naturally going to the consequence of the rule, we just consider the next occurrence to be some assumption discharged by the elimination rule, and just go on from there towards the conclusion. And we have another track in which we start here again at the major premise of elimination, and then go to the other assumption being discharged and go on to the conclusion, so on and so forth. And here at the two tracks on the right, perhaps it's better, we see this kind of very nice shape or hourglass shape of the tracks assume in normal derivations, where we have first major premises, occurrences of major premises of elimination, and then the complexity decreases until we reach a so-called base segment here, highlighted in bold, and then we have premises of introductions, and the complexity increases again. Right. So with that out of the way, I think we are in a good position to see one of the core notions of our semantics, which is this concept of a canonical track. I think the best way to understand it is just to think of the usual tracks and then just take the analytic part. And I quickly introduce some terminology. So in the last segment in a canonical track, that is the base segment, if you will, is atomic, then we call the track exhaustive. So here's an example. This here is a canonical argument, what we are going to call a canonical argument, because it has main canonical tracks. So in particular, we have a canonical track here that starts with this occurrence, this major premise of elimination, and then goes on to this B implies C here, this occurrence here, and then finally goes on to this segment here, which is composed of 3 occurrences of C. Now, the canonical track, what we are calling a canonical track, actually ends with the analytic part, so with the last segment that is a consequence of an elimination rule, but the argument may proceed after that towards some consequence by means of any kind of arbitrary arguments, or arbitrary inferences. And of course, the canonical inferences we may think are automatically valid because they are self-justifying or using our rules that determine the meaning of the logical constants. But a canonical argument may also have this non-canonical part, this part made out of arbitrary inferences. And so for a canonical argument to be valid, we need that the non-canonical parts are also valid, so that the validity of a canonical argument depends on the validity of its non-canonical parts. Right. So now we can state the definition of validity more precisely. We come from our rough idea of our rough presentation from before. And we now say that we assess what can be extracted from a conclusion by doing what I'm calling here unfolding the argument. What I mean by that is we just take the argument and exhaustively apply eliminations to the conclusion G, and then we follow that up with some valid inferences until we arrive at some consequence. Now, you may have noticed that we have here some kind of interdependence between the notion of an arbitrarily valid argument and a canonically valid argument, so that we have some kind of double induction going on. And this means that we have to take extra care in order to ensure that the definition of validity is well-founded. And we do that just basically by imposing some complexity requirement on the unfoldings. So basically, you can think of that as just requiring that the final consequence of the unfolding is not more complex than the original conclusion G. So it's has at most the complexity of G itself. And now we have the same picture from before, and we can say more precisely that an argument is valid if and only if for any unfolding, such as the one we have on the left here, depicted here on the left, where we have these exhaustive canonical tracks and then some valid non-canonical part to some consequence Zi. So for any such unfolding, we have a way to get a valid canonical argument, such as the one on the right, where we end with the same conclusion of the unfolding, that is Zi, and we do that under this exact same assumptions of the unfolding, that is from gamma and possibly delta I. And the fact that we preserve the exact same multi-set of assumptions is what gives this notion of validity its substructural character. Right. So perhaps a very simple toy example, so that's to make this a little bit more concrete. So let's say we have an argument here inside the box. This is distribution of conjunction, multiplicative conjunction over additive disjunction. So we may think that any unfolding of this argument may take like this general form here, depicted here, is where we have the eliminations, we apply the eliminations, then we have some valid arbitrary argument A1 and another one A2, which converge into a single consequence Z. And from that, we can indeed construct a valid canonical argument, but now from the assumption of the original argument, we just apply the eliminations and we plug in the A1 and the A2 here, such that we have, again, Z now under the exact same multi-set of assumptions as before. Right. So I thought it would be instructive to give you some intuitions about the adequacy proofs. And I think the proofs of soundness and completeness can be seen as a way to cash out some local notion of harmony. A notion of harmony which is conceived in terms of so-called conversions. So a good place to read about harmony in terms of conversions is the first chapter of this recent book by Tranchini. And the basic idea is, for soundness, we are going to leverage the so-called beta reductions, or beta reductions, however you want to call it. Here I'm displaying just some sample of these conversions dealing with the connective, the additive disjunction. So here from left to right, we have a so-called beta reduction. And we are going to leverage these beta reductions in order to show soundness. This is very common, I would say. So in the literature, this is usually the way that we show soundness, at least when we have this kind of argument structures or skeletons in the semantics. Perhaps I should sound a word of warning, or remark rather, that the side assumptions here are shared between the two minor premises of elimination, such that when we do the beta reduction and we throw D3 away, we are not actually messing with the overall multi-set of assumptions. This is important in a substructural setting, that all the convergence pay attention to this. What is perhaps not so often remarked upon is the relationship between eta expansion and completeness. So for our proof of completeness, we are going to be leveraging the eta expansions, which is the transformation shown here at the bottom that goes from the right to the left. So we basically, if we have some occurrence of a complex formula inside some structure, some tree structure, such as this one, A or B, we can then eta expand in this way, where we just start with A or B, then apply introductions, then eliminations, and we just go to A or B again. And now we have a base segment that is less complex. Right. So soundness. For soundness, we are given a derivation, and we need to show that it is actually valid. So let's start with taking some derivation of G from gamma, and we've taken a derivation in so-called expanded normal form. That is a normal derivation where in all the tracks, the base segment is atomic. And we then unfold the derivation, and we have then a situation as similar to what we have here. So on the left, we have the unfolding. On the right is what we need to get, so a valid canonical argument such as the one on the right here. This is what is required by the definition of validity. So we have actually our mission is to come up with this element in the middle here. So some way to get from the left to right, some transformation or some kind of construction or function. And we do that the following way. So if we focus on the main tracks and we look at G here, we see that it is a redax. So it's a redax because we can, in the sense that we can beta reduce it or beta reduce it, because it is both the consequence of an introduction, because it is a member of the synthetic part of the derivation, and it is also a major premise of elimination because it is a member of the canonical track, the exhaustive canonical track of the unfolding. So we just beta reduce it, and as necessary, we just keep beta reducing until the synthetic part of the original of the derivation cancels out with the exhaustive canonical track of the unfolding. And in this way, we just copy over the non-canonical part, and in this way, you get exactly a valid canonical argument as the one on the right that is required. So this is for the main tracks. We may need eventually to go up to tracks of higher order and just repeat the process again. So the argument is actually by induction on, the proof is by induction on the order of the tracks. And this is okay. So this is usually the way it's done. People sometimes don't even bother proving this in detail. For completeness, we are given a valid argument, and we need to show that it is actually derivable. So let's imagine we have a valid argument here from gamma to G. Now, since we are given that the argument is valid, we already have this transformation here that takes us from whatever unfolding is on the left and gives us something appropriate on the right. So the mission in the completeness proof is actually quite different. We actually have to select an appropriate unfolding on the left such that the transformation will give us the desired derivation on the right, or something very close to a derivation. Because this transformation, since the argument is valid, this transformation gets us something on the right form for any unfolding we may have on the left. This is what the definition of validity says. And here we consider what I'm calling here the emblematic unfolding, where we just apply eta expansions to the conclusion G. So we just fully eta expand G. So we apply an eta expansion to G, and then we look at the tracks. If there's still some complex base segment, we just eta expand again, and so on and so forth, until all the base segments are atomic. And this is a legal unfolding because the non-canonical part, so this other part here after the canonical track, is valid. We know that it is valid because of soundness. And we notice also that the delta here is either, in the case of this particular unfolding, the delta here is empty or discharged. And the final consequence of the unfolding is actually G itself, so that we are not violating our complexity requirement. So we may think of this emblematic unfolding as some kind of like unfolding a piece of cloth. So we start with G, and we just keep the G, but kind of unfold it into its component parts in the middle. And for this unfolding in particular, so what we get on the right is actually the desired derivation, because we don't have any deltas. So we will get a valid canonical argument for G, which the conclusion is G itself. And so the non-canonical parts, which are actually a synthetic part of the derivation, gets copied over to the right. And of course, this is an argument that applies to the main tracks, and we may need to do the same reasoning for tracks of higher order, such that we have a complete derivation on the right. Okay. So I would like to make some remarks in order to perhaps make the use of eta expansions in the proof of completeness a little bit more clear. And I would like to do this by means of an illustration, so discussing an example, or counterexample rather. And for that, I chose an example that is actually not related to substructural logics. I had one for substructural logics as well, but I had to cut it out because of time constraints. So I'm going to see the one that is related to some incompleteness phenomena for some target logics in PTS, in Proof-Theoretic Semantics, and this is somehow known as the split rule. There is this paper by Pesla, which discusses the split rule in details. And this rule or argument is underivable in intuitionistic or minimal logic. So we are going to see the case of this rule for minimal logic. So this is we can think of the notion of validity from the point of view of the completeness proof as kind of matching eta expansions of the conclusion with eta expansions of the assumptions, so to say. So if we look here, we consider the eta expansion for the conclusion of the split rule. So the split rule is kind of the distribution of implication over disjunction. I'm showing here the standard implication and disjunction with the usual rules. Of course, if we substitute the corresponding substructural connectives here, this is also not derivable. But for simplicity's sake, let's just look at the case for minimal logic instead. And here we have here a yet expansion. So we start with the conclusion here, this occurrence of the conclusion of the split rule, just eliminate and then introduce back again in order to get the same thing as before. And we may abstract away from the non-elimination parts. So just say we have some arbitrary argument, valid argument A1 here and A2 here. So we are only showing the elimination rules. And this will be something that is on the emblematic unfolding. So this is what we substitute for the conclusion in this, what I was calling the emblematic unfolding. And now if we look at the eta expansion for the premise of the split rule, or the assumption of the split rule, we have something like this. And we can see that here that the A, this discharge assumption A here, remains outside the dilemma between B and C in the minor premise of elimination there. And this is such that we can't actually get, there is no function that will get us from what's on the top to what we would desire using the analytic part of the eta expansion on the bottom. The best we can do is this. So we just plug in A1 here and A2, and we get the desired conclusion. And we have available a discharge for A inside A1 and inside A2. However, the assumption A itself remains outside the dilemma and out of reach of these discharges available in A1 and A2, such that in the best scenario, A remains here as an additional assumption undischarged. And this is basically the counterexample to the split rule, the fact that we can't do away with this additional assumption A. Let's see how we're doing. Oh. So I would like to finish then with some comments, some comparisons between our approach and base extension semantics, or BES. I will start with, so base extension semantics can also be seen, I guess, as a semantics based on the elimination rules, or at least some people have remarked upon this fact because of the particular clause that we have for disjunction, which is similar to the elimination rule for disjunction. So in this sense, it is very similar to the approach we are proposing here, but there are some small differences. And I'm going to start with what I see, at least, as disadvantages of our approach compared with specifically with base extension semantics. The first disadvantage is, at least in my opinion, is that we deal with arguments and transformations between arguments. And this is kind of annoying. I would say, oh, can you hear me?
Yes.
Oh. So this is, I would say this is kind of annoying. So many people, myself included, would prefer to have a more neater semantics with linear clauses stating some necessary and sufficient conditions for each one of the constants and so on. One might wonder whether these arguments and transformations between arguments is actually essential. My impression is that they are not. However, I haven't really thought this through. So it is what it is at the moment. So we are stuck with arguments and transformations between arguments. And I see that as a disadvantage at least. Another disadvantage is that we have very loose ties to BHK. So if you're looking for constructive semantics and you share the widespread view that BHK is kind of the standard against which constructive semantics should be measured, so that any constructive semantics should somehow heed to BHK, that it's not clear how our proposal relates to BHK, or at least it doesn't relate as closely as the standard proposals, where we have the placeholder view of assumptions, for instance, and the usual clauses for the constants inspired by the introduction rules. And another disadvantage is that we don't have bases. So we could have bases, so we could add those bases, but they make no difference whatsoever to logical validity. And as a result, our notion of counterexamples are somewhat unfamiliar. So as we just saw with the example we discussed, the counterexamples actually involve the failure of some transformation, or we can point out to some assumptions that we can do without. Of course, these assumptions may be related to something which is more familiar as a counterexample, but this is very many steps away from what we have when we actually incorporate the bases. So when we have bases, we can just say, well, just take the base. The base is the counterexample. So look at this base. So this base here, we have a proof of the assumptions, but we don't have a proof of the conclusion. So we can actually show the base. And this I consider to be something much more familiar. Now, for what I consider to be advantages of our approach. So on the one hand, it is kind of a bummer that we don't have bases. But on the other hand, yay, we don't have bases. Or rather, I should say we don't need bases. So this comes also with some positive effects, I would say. One of them being that our notion of logical validity is a direct upshot of the elimination rules. I think there is an argument to be made that logical validity should not depend on the format of the bases, whether we allow this or that on the base, or what kind of base we have. So if we tweak the base a little bit, we get one logic. If another kind of base, we get a different logic. I think there may be an argument to be made that logical validity should depend solely on the meaning of the logical constants and be independent or somehow agnostic with respect to the base. And we have this in our semantics. Another positive point that is also related with our independence of bases, that we have a simpler notion of support. So we just have the notion of support that is intended to capture the target logic, and we don't need to generalize over bases. Or more specifically, if we compare our approach with a recent proposal by Giorgio and co-authors for a proof-theoretic semantics intended to capture a substructural logic as well, and their PTS is inspired by base extension semantics. There we have this kind of support with two indices. So we have an index for the base, and we have another index for S for the resources. And this is kind of unavoidable, because since in BES we have this placeholder view of assumptions, then we're gonna eventually kind of dilute the assumptions inside the base, so they get diluted in the base, and then they are not resources anymore. So we need this kind of index in order to keep track of the resources, and then we have to generalize over the base and then generalize again over the resource. And in contrast, this is somewhat more complicated if we contrast it with our notion of support. It's just a simple notion of support. The resources are actually just the assumptions themselves. And finally, we have this so-called base completeness, in the sense described in a recent paper by Piccolomini d'Aragona. What this says is that, what I mean by that is that if we were to supplement our notion of support with some rules, for some atomic rules that we may consider constitutes a base, then if we have validity inside the space from gamma to G, then we actually, in the syntax, in the system, in the syntactic system, we get there is a derivation actually of G from gamma by just including the rules, the basic rules, together with the rules for the target logic. And this is something that fails for base extensive semantics. So we can actually have an example of something that is valid inside a particular base, but if we take the target logic and add the rules of the base, we don't actually derive the desired conclusion. And well, this is it for me. These are the references that I'm citing in the slides. Thank you very much for your attention, and I hope you have questions.